in the example building. This course also briefly covers the design of industrial structures and its peculiarities. Once the design is completed, drawings are required for the construction of the building. We have briefly covered about the various structural drawings required for construction of structural steel buildings like good for construction or GFC drawings, fabrication drawings, erection drawings, and various details covered in each of them. Fabrication, transportation and erection of structural elements are important steps or activities in the structural steel building construction. These aspects are also covered in this course along with various inspection methods and good construction practices. In a nutshell, we can assure you that this course will cover comprehensively the various design and associated aspects a structural engineer should know for efficiently designing and constructing structural steel buildings. Thank you. Welcome to the course on construction aspects of steel buildings, where we will delve into the nuts and bolts of building with steel. We'll start with the heart of it, connections. Shear, moment and splice connections form the backbone of our structures. We'll discuss the design actions and explore examples for clarity. Designing connections is an art. We'll walk through the design of beam-to-beam connections, beam-to-column connections and splice connections, ensuring they are not just strong but smartly designed. After discussing the design of conventional steel buildings, we'll explore industrial buildings. From framing structures to roofing and wall materials, the essentials are also covered next. Every building carries a load, and in industrial settings, cranes and mezzanine floors are the game changers. We'll evaluate the loads because of these actions and dive into their design. Plate girders are the workhorses. We'll design them step by step and explore the features and selection criteria for using them as gantry girders. In the world of industrial structures, laced and batten columns play a crucial role. We will look into their design in detail, covering various scenarios. The blueprint of any structure is in its drawings. We'll plan the structural drawings, delve into the fabrication procedures, and discuss the transportation logistics. Putting it all together requires careful planning. We'll go through erection planning, step-by-step structure assembly, and the necessary inspections for a smooth construction process. As we wrap up, we'll emphasize good design, detailing, and construction practices. Join us in this exploration of construction aspects in steel buildings. We are not just building structures, we are crafting a legacy of robust, efficient, and well-designed steel marvels. Let's build excellence together. Happy learning. In this topic, you will see in detail about the connection elements, connection types, and the various connections required in structural steel buildings. We all know that buildings are composed of many structural elements joined together generally by bolting or welding. These joints or connections have to be appropriately designed so that the structure acts as a single integral unit. That is, connections are the crucial elements in building structures that govern their strength, stiffness, and stability. It is important to identify the type of connection to be provided for each element based on the behavior required for that member as well as for the overall structure. Now, let us see the shear stress and bending stress diagram for the I sections. The shear stress distribution is generally referred to as top hat distribution as it resembles the same. The bending stress distribution is a triangle like this. From this behavior of I section, it can be clearly seen that the bending stress is maximum in flanges where it has got relatively much more area to resist it, and shear stress is maximum in the web area. Bending stress is carried by the top and bottom flanges and the web bears most of the shear stress. It can be said that most of the shearing stress, usually about 95%, is carried by the web. For this type of shear distribution, the shear connection is generally done using connecting elements. The shear force acting from the web of the supported member is transferred to the connecting element like fin plate or cleat angles, etc. by bolts or welds. Further, the connecting element transfers this shear force to the supporting element without any shear failure. Also, in the case of bending, it can be seen that the moments are majorly taken up by the flanges, generally more than 90%. Hence, in this type of moment action, the flanges must be connected with suitable connecting elements for effective moment transfer. For example, in the case of beam column junction in a moment resisting frame, the junction experiences moments, which is usually transferred via direct welding of beam flanges to the column web or to the flange, or by means of top and bottom flange plates with bolts. We all know that the various connecting elements used in structural steel buildings are bolting, welding and riveting. Of these, the most commonly used are bolting and welding. We have already seen the various types of bolts like black bolts, HSFG bolts, etc. We have also seen the different grades and diameters of bolts as well. According to the requirement of the connection, a suitable bolt type, diameter and grade have to be chosen for the connection. There are different types of welding as well as grades of welds available for joining structural steel elements. We have looked into some of these grades in our previous topics. Rivets are another type of connecting element which however are not generally used in buildings these days. The suitable connection type like welded, bolted or riveted is selected based on various aspects like structural requirement, easiness of fabrication and erection and overall cost. Depending on the type of forces to be transferred by the connecting element to the supporting element, there are mainly two types of connections. The first one is a shear connection, wherein only the shear and axial force from the member will be transferred through the connection to the supporting element. The second type is moment connection, where in addition to the shear force and axial force, moments have to be transferred from the supported element to the supporting element. As you are aware, we choose either shear or moment connections for connecting each element depending on the forces to be transferred, strength, stiffness and stability aspects, fabrication, transportation, erection and economy aspects as well. We will look into some of the main shear and moment connections used in structural steel buildings in the subsequent topics. Connections in structural steel buildings can be from structural steel to structural steel elements, structural steel to concrete elements, and it can be even glass and aluminum with structural steel elements. Let us look briefly into the various connections in buildings in the general order of execution. The connections in structural steel buildings generally start with the base plate to the foundation or pedestal using anchor bolts. We have seen some connections of the base plate using anchor bolts in the previous topics. This connection has to be designed to transfer the total building forces coming on each column to its foundation. The next connection is the connection of the column with the base plate. These are generally welded connections with or without stiffeners connecting the column to the base plate. The selection of this connection type depends on the idealization of the connection, which is pinned or fixed, the force to be transferred from the column to the foundation, and practical considerations like fabrication and erection. Once the column with the base plate is erected, the next set of connections will be generally for the braces if it is a braced building, or beams in the case of moment resisting frames. In some of the braced buildings, the bracing connection can be to the beam as well as to the column. In such cases, the beam connection with the column will have to be done prior to the brace connection. So, let us look into the beam to column connection first. Depending on the type of connection planned for the beam with the column, that is shear or moment connection, an appropriate connection type has to be chosen and designed according to the requirement. There are different kinds of connections possible for the beam to column connections. Generally, shear connections are used for connecting the beam to column when only vertical load has to be transferred from the beam to the column. That is, the beam and column need not have to form a moment resisting frame to take the lateral load acting on the structure. As we have already learned, in moment resisting frames, beam to column connections have to be moment connections. These connections can be either bolted or welded. selected based on the various factors we have mentioned earlier. We will look into the various beam to column connections in the subsequent topics. Beam to beam connections are the most used connections in buildings generally. These connections can be between the secondary beam to the primary beam or tertiary beam to the secondary beams or even between the tertiary beams. Shear connections are generally used for these kinds of beam to beam connections in general. However, as we have seen in the previous module, there can be cases wherein moment connections are used for beam to beam connections. For example, in the case of backup beam requirements. We will have a brief look into the various beam to beam connections in the subsequent topics of this module. We know that braces are the lateral load resisting elements in structures, and we have learned that bracing elements can be subjected to even change in nature of force, that is tension to compression and compression to tension, due to the reversal of direction of lateral forces acting in the building. Braces are generally connected to the columns or beams or to the interface of beam and column. Gusset connections are usually used for the connection of bracing elements with beams or columns. The connection of bracing elements at the intersection of X braces is another type of connection required generally. Apart from the braces which can undergo tension when resisting the lateral loads, there can be other tension members also in the building structures like truss elements, tie rods, supports of hanging platforms, etc. Shear connections are generally used for connections in tension members. When the length of the beam or height of the column is more than the available single section length, or otherwise when it is more than the maximum transportable length, we have to connect multiple elements to make a column or beam. The connection between these elements is called splices. Splices are required when there is a size change for the members along its length as well. Splices are designed for transferring the forces between these two segments at the splice location. That is, the splices can be either moment connection or shear connection. We will see some of the splice connections used in beams and columns in the subsequent topic. As we have already seen in the topic service integration in buildings, the building structure has to support different services and architectural features. It is important to plan the connection of these elements or the substructures supporting these elements with the main structural steel elements. Connections for equipment support, combined service line supports, facade supports, etc. are some examples of such connections. Now, let us summarize all that you have learned on this topic so far. Various connecting elements generally used in structural steel buildings are welds, bolts and rivets. Most of the connections used in buildings fall under either shear or moment connections. The major connections in structural steel buildings are column to base plate, beam to column, beam to beam, brace to beam or column and splice connections. Connections for supports of services and architectural elements are also important in building structures. By this, we have come to the end of this. Topic. Let us meet in another interesting session. Thank you, learners.
At the end of this topic, you should be able to describe about some of the main shear connections used in structural steel buildings. We have already learned that Connections are an integral part of any structure, and based on their behavior or the forces it transfers, it is mainly classified into shear connections and moment connections. Shear connections will transfer only shear and axial forces from the supported member to the supporting member, and in moment connections, in addition to these forces, it will transfer the moments as well. From the behavior point of view, shear connections are pinned connections where the connected elements are free to rotate about a connection point, and in moment connections, the relative rotation between the connected elements are zero. Shear connections are a widely used connection type in buildings for connecting the beam to column, bracing elements, tie rods, purlins, service supports, etc. These are made using bolted and welded connections. Let us look into some of the commonly used beam-to-beam connections next. Beam-to-beam connections can be between the primary and secondary beams or between the tertiary and secondary beams. In both these cases, when the beam behavior is assumed as simply supported, we have to identify the most suitable shear connection between the elements considering the various aspects we have already discussed like strength, easiness of fabrication and erection, overall economy, etc. Cleat angle connections are the most commonly used shear connections between beam to beam and beam to the column. An angle section called cleat is used here to connect the supported beam to the supporting beam. One leg of the cleat will be connected to the supported beam and the other leg will be connected to the supporting beam. These connections are done using either bolting or welding or even a combination of both. As in the case of any connection, the size of the connecting element, its grade, arrangement, etc. will depend on the force to be transferred, sizes of the connecting elements, connection location, orientation of these elements, erection feasibility, etc. The selection of the connecting element like bolt or weld depends on factors like time, availability of skilled labor, feasibility of execution, etc. When these connections are done with the cleat on one side of the connected element, it is called a single cleat connection or single angle connection. When it is done with cleats on both sides of the supported element, it is called double cleat connection or double angle connection. Here, the supported beam is connected to the supporting beam using a single cleat and bolt on both the legs of the cleat. In this case, you can see double cleats and bolts that are used to connect a secondary beam to a primary beam. You can note here that in these kinds of connections, the supported beam will have to be notched to enable the connection. Inside fin plate connection is another commonly used shear connection between the secondary beam to primary beam or tertiary beam to secondary beams. In this case, a fin plate is welded to the main beam and the supported beam is connected to this fin plate using either welding or bolting. The fin plate generally will have enough width for connecting the supported beam. The depth of the fin plate can be covering only the partial depth of the supporting beam or the full depth of the supporting beam depending on the size of the supported beam as well as the quantum of force to be transferred. When a full depth fin plate is provided, it is welded to the web and flanges of the supporting beam. In this type of connection, the supported beam flange or flanges have to be notched to enable its connection with the fin plate. Extended fin plate connections are one of the commonly used shear connections between beams. As we can see in this image, a fin plate is connected to the supporting member using a weld with an extension of the fin plate projecting beyond the flange edge. The connection of the supported element to the connecting element is done through bolting of the supported element's web with the extension of the fin plate beyond connecting element flange edge. We can have either the full fin plate extending beyond the supporting beam flange line like this, or only the part of the fin plate extending beyond the flange line like this, depending on the depth of the supported beam. The connection between the supported beam with the fin plate can be done using welding also. The major advantages of this connection are: the fin plate can be cut to shape with the required bolt holes in it, and it can be welded to supporting element at the fabrication yard or factory itself. The supported beam, that is the beam that has to be connected to the main beam, can have straight cuts at the ends, which reduces the fabrication efforts required. The supported beam can be erected easily by lowering the beam vertically at its position between the supporting beams, which is not possible if the supported beam length is more than the distance between the flanges of the supporting beam. Another type of shear connection used for connecting secondary beams to primary beams is the end plate connection. In these types of connections, a stiffened or unstiffened end plate is connected between the top and bottom flanges of the supporting beam for easy connection of the supported beam to the supporting beam. The requirement of stiffener for the plate connected to the supporting beam depends on the size of connecting beams and the amount of shear force to be transferred. The major advantages of this connection are: the end plates on the supported beam and the supporting beam can be welded to these beams at the fabrication yard itself and at the site. Only bolting is required between these plates. There is no notching requirement for the supporting beam. The beams can be erected easily by lowering vertically in its position, that is, tilting of the beam in the plan to bring it in its position is not required as in the case of cleat angle connections and inside fin plate connections. Direct welding of the web of the supported beam to the supporting beam is another type of shear connection. This type of connection is not very commonly used in practice, as there is hardly any fabrication tolerance, as well as the erection is difficult with the precise fitting requirement. As the connection name indicates, in this type of connection, the web of the supported beam is directly welded to the web of the supporting beam. We have seen some of the most commonly used beam-to-beam shear connections so far. Let us look into the beam-to-column shear connections next. Beams can be connected to columns using single or double angle cleats, as in the case of beam-to-beam connections. These connections can be made using bolt or weld depending on the type of sections connected, as well as the other fabrication and erection aspects. For example, when the column sections are closed sections like a box or hollow sections, normally we will use welding to connect the cleat angle to these columns. Similar to the beam-to-beam connection using a fin plate, a shear connection of beams with the columns is also possible using fin plates. These fin plates are welded to the flange or web of the column to connect the supported beam. The connection of the supported beam with the fin plate can be either bolted or welded. When a beam has to be connected to the web of I-section columns, it is easier to provide a faceplate on the column with a fin plate on it. This will ease the fabrication and erection of beams, as it doesn't need any notching of the beam. The fin plate to beam connection can be done either using welding or bolting. This type of connection can be used for beam-to-beam connections as well. These connections are similar to that of beam-to-beam welded shear connection, where only the web of the supported beam is welded to the supporting column web or flange. Like in the case of such connections in beam-to-beam, here also a perfect fit of the connecting elements is necessary for the proper execution of connections. In this type of beam-to-column connection, plates are welded to the ends of the beam and bolt holes are provided in these end plates. Aligned bolt holes are provided in the column as well. All these works are done at the factory, and hence only the bolting process has to be done at the site. This is one of the key advantages of these types of connections. These kind of connections are used for connecting the beam to both the flange and web of the columns. Let us summarize all that you have learned. Some of the commonly used shear connections are between beams as well as between beam and column. Cleat angle connections, inside fin plate connections, extended fin plate connections, end plate connections, direct welding of the web are the commonly used beam-to-beam shear connections. Cleat angle connections, fin plate connections, a face plate with fin plate connections, direct welding of the web, end plate with bolted web are some of the commonly used beam-to-column shear connections. At the end of this topic, you should be able to describe some of the commonly used moment connections in structural steel buildings. We have already seen about the importance of connections and various commonly used shear connections in structural steel buildings. As we have seen in the previous topic, in the case of moment connections, in order to transfer the shear force and bending moment from the supported element to the supporting element, the flow of force from both the web and flanges has to be ensured between these elements. Moment connections are made using bolting, welding and riveting. As in the case of shear connections, riveting is not commonly used in practice these days for the moment connections in buildings. Moment connections are predominantly used for the beam to column connections in structural steel buildings. We have seen special cases like backup beams where moment connections are used for the secondary beam to primary beam connections as well. Let us look into the beam to column moment connections first. There are many types of moment connections possible between beams to columns. Fully welded, extended end plate with column stiffness, etc. are some of the most commonly used beam to column moment connections. As the name indicates, the whole beam cross-section is welded to the column to ensure the flow of force from both flanges and the web of the beam to the column. In the case of the beam to column flange connections, these connections are easy to fabricate and erect. If you look at the normal erection plan, a beam which is cut to its precise length has to be brought between the columns to which it is going to get connected, and then it is welded to the columns at both ends. However, this method has two constraints from a practical execution point of view. The first one is that the beam length has to precisely match the distance between the column flanges, which does not give any erection tolerance. The second issue is that we have to do the welding at the site, which will be more time consuming, as well as it will require temporary support for more time. To avoid these constraints, generally part of the beam is welded to the column as a beam stub at the factory itself, and the segment of the beam between the beam stubs at both the ends is joined through a bolted splice. In this way, a faster, better quality control welding can be done at the factory between the beam and column, and at the same time, since the splices are connected using bolting, it can be done faster at the site. Depending on the forces to be transferred from the beam to the column, as well as the properties of the column section, sometimes backing stiffeners are provided within the column based on the requirement. Extended end plate connection is another type of moment connection between the beams and columns. In this case, an end plate extending beyond the flange outer lines is welded to the beam ends, and the connection between this end plate and column is done using bolting or welding. In the case of open section columns like I sections, bolted extended end plate connections are generally preferred. However, in the case of closed section columns like box section, extended end plates are welded to the column face. In some of the connections, the extended portion of the end plates is stiffened like this. These connections are similar to that of extended end plate connections but are provided with additional stiffeners in the column based on the requirement. Generally, these column stiffeners are aligned along the top and bottom flange lines. In some cases, diagonal stiffeners are also provided within this joint region of the column to avoid panel zone buckling of the column web. That is, all these stiffener requirements will be based on column element properties as well as the loads to be transferred. In the beam to column connections we have seen so far, the column will be continuous and the beams are attached to the column. However, in some cases, the beam or plates in line with the beam flanges and web are taken through and the column is continued over the top flange plate of the beam section. This type of beam to column moment connection is generally used when hollow sections are used as columns. In this case, the flange plates of the beam are connected to the external collar plates provided around the steel column. These types of connections are also generally used for hollow section column cases. As we have already discussed, beam-to-beam moment connections is not very frequently used. However, when it is used, attention has to be given to the supporting beam's torsional capacity, especially when open sections like I sections are used as supporting beams. It can be used with an open section of supporting beams where we have moments from supported beams on either side, and the majority of these moments get balanced with each other. Let us have a quick look at some of the commonly used beam-to-beam moment connections. In this type of connection, the supported beam is welded to the supporting beam with flanges of beams aligning in the same line. However, this is only possible when we have the supporting and supported beams have got the same depth. Another possibility for such fully welded connections is when we have a relatively much smaller section beam with a smaller amount of moment that has to be connected to the supporting beam. In this case, generally the top flange of both the supported and supporting beams are aligned together and welded. The bottom flange of the supported beam is then welded to the web of the supporting beam. However, you have to note that the beam top levels are decided based on the requirement. This type of connection is generally adopted when we have secondary beams connected from both sides of primary beams. These types of connections are used when we have secondary beams connected on either side of the primary beam. In these cases, with or without weld between secondary and primary beam flange plates on the tension side, an additional flange plate is provided connecting both the secondary beam flanges at that location. When we have same-sized beams subjected to reversal of bending moment connected together using moment connection, additional flange plates are used on both the top and bottom flange plates. These additional plates used for connecting the flanges are called cover plates. These cover plates can be welded or bolted with the supported beams. Let us summarize all that you have learned. The commonly used beam to column moment connections are fully welded, extended end plate with column stiffeners, and collared plate connections. Beam to beam moment connections generally used in structural steel buildings are fully welded and cover plate connections. Aligning connecting